For the following alcohols, we're asked to determine the degree of substitution and the type of product it will form once it undergoes an oxidation reaction. So in the first case here, we have an OH group on this carbon here, and this is a primary carbon. So essentially we have one R group attached to this carbon, plus we have the alcohol functional group. So this is a primary alcohol functional group. Here on this, we have an alcohol functional group on a carbon with two carbons attached, so this is a secondary carbon, and here we have another primary carbon, very similar to this. We have a carbon with one carbon attached to that one, so this one also is primary. Alright, and then the product of the oxidation reaction, this is interesting because carboxylic acid, if we fully oxidize a primary alcohol, will form a carboxylic acid. Since we don't have that option, this can't form a ketone for sure, so when we form our double bond right there, we only have one carbon attached to it, so this has to be an aldehyde functional group. Again, if we had a strong enough oxidizing agent, then the best answer here would be a carboxylic acid. Here we have two carbons attached to what will be carbonyl carbon, so this is going to be a ketone. And here this is going to be another aldehyde functional group based on our options. But again, this primary alcohol could be converted to a carboxylic acid if we have a strong enough oxidizing agent. Alright, going through the rest of them, so this one's similar to the center one above where we have secondary, making this a ketone. Here, if we think about this being a carbonyl carbon, that would be impossible because we have three carbons attached to it. So if that's sp2 hybridized, we have a double bond right there, we can only have two additional carbons attached. So this one is a tertiary alcohol and no reaction is possible. We cannot oxidize this to form a ketone on here because we don't have enough basically empty space. We don't have the extra hydrogen there to form our ketone functional group. And then same thing for this one. This one is also tertiary and no reaction. Alright, for the next set, for our reactions, show the product undergoing oxidation. So we will say oxidation here. Basically for all of the, I'm not going to fill in all of them, but say an oxidation reaction. In this case, actually, I'm going to put oxidation for these. So these, if we do an oxidation reaction on these, based on what we talked about above, then we would get our ketone there, and for A, we would get an aldehyde functional group. So an aldehyde functional group. Here, if we attempt to do any oxidation reaction, we would not get anything here. So I'm going to say no reaction. All right, for these, let's be a little bit more specific. So let's go ahead and use a strong oxidizing agent in this case. So H2Cr2O4, and let's use. And these wouldn't matter if we used either one. So if this one we use bleach, we'd get the same product as if we use the strong oxidizing agent. So we'll just say oxidizing agent for these. If we oxidize that, we end up with a ketone functional group. And for this one, we get no reaction. So no reaction for oxidizing agent. For this one, if we use a strong oxidizing agent, we actually end up with a carboxylic acid. Now for this, if we would have used bleach, so if we would have used our HOCl for bleach, we would have actually stopped at our aldehyde functional group. So in that case, the product would have been that compound there. Now this aldehyde can be further oxidized, so if we were to treat this reagent with something strong like chromic acid, we could end up getting to this product. Not we could, we would end up getting to that product. Anyway, for the homework, all I was really looking for was the aldehyde functional group. If you showed the carboxylic acid, that'd be fine too. But that's good to be aware of because you need to know basically what chromic acid, also what bleach will do with our alcohols. All right, so for these, we're asked to draw a mechanism showing bleach reacting with our alcohol, and here we have a secondary, here we have a primary. So for the reaction with bleach, the first thing we're going to do is use our electrons on our oxygen to make a better leaving group. So now we have OH2 with a plus charge. We not only have a better leaving group, but we also have a much stronger nucleophile. So our other product of this is an oxygen with a negative charge on it, and that's still attached to the chlorine. So now we can do an SN2 reaction where we do our attack and kick off the leaving group simultaneously, and that gets us to our next intermediate, which now we have oxygen and chlorine both attached here. And in the last step, we need a base to deprotonate this proton, form our double bond, and kick off our good leaving group, chlorine. So I'm going to write in a base, and we would probably add this into the workup. So something like 3 molar sodium hydroxide to deprotonate that, form our double bond, form our ketone functional group, and kick off the leaving group. So our final product is that ketone. We haven't covered this chapter yet, but this would be butane as our parent chain, and then our ketones at the 2 position, so butane 2-one. All right, for the next one, we have a primary alcohol. The mechanism is remarkably similar, where we're going to protonate our alcohol first. So now we have OH2 plus charge on it, and now our other byproduct that we made is OCl with a negative charge on it. That's going to come in and do an SN2 reaction, kick off our leaving group, and now we have our carbon chain with OCl attached to that. Let me emphasize on this. So on this previous question and on this question, I didn't emphasize the backside attack. In this case, it doesn't matter because we're going to form a carbonyl carbon there anyway. So this carbon will not be a stereocenter, so it really doesn't matter in this case whether or not you emphasize the backside attack. All right, for the next step, after we kick off our leaving group, we have water, we have our OCl attached, so now we need to use a base to deprotonate one of these hydrogens, form our double bond. In this case, we're forming a carbon-oxygen double bond, which is not a ketone, it's an aldehyde functional group, because we still have a hydrogen attached to that carbon rather than another carbon. So once we deprotonate that, we get our final product, which is now our aldehyde functional group and the hydrogen. So this is our final product. This is what that gets us to. For this reaction, so this hydrogen right here, which I did not deprotonate, is that hydrogen right there. I have my carbon double bond oxygen, which is what I showed forming here. So this is my carbon double bond oxygen that's shown right there. And then another byproduct, if you wanted to put, you could say HB. In this case, I didn't have a charge on the B, so I'd have a plus charge. And then one other byproduct would be water. All right, for the next, we're going to name the following compounds. So it's similar as we did with our alkanes, except the alcohol is now the parent. So instead of alkane, it's essentially alcohol, which, let's look at the actual parent chain and think about that. So we got carbon number 1, 2, 3, 4, 5, 6, 7. So it's heptane. So we're going to take off the E and add an OL. So this is heptanol. So instead of heptane, we're going to take off the E and add an OL, which means we have our alcohol functional group. Now for numbering where that is, we can put the number right in front of that OL, or we can put it in front of the parent carbon chain. So 1, 2, 3, 4, that's at the 4 position. So 4 heptanol, and then we also have a methyl at carbon number 1, 2, 3. So this is 3 methyl for heptanol, and we also need to specify the stereocenters. So in this case, our stereocenters are specified, so we need to say what they are. So for this one here, we have a hydrogen in front. I'm going to leave it in front, and for the rankings, we've got 1, 2, and 3. So it looks like we have a clockwise rotation. However, 4 is not in the back, so that's going to be an S stereocenter. So we've got 4S. And then for the other one here, I'll erase this stuff. For this stereocenter here, fortunately 4 is in the back, so I'm going to draw my hydrogen in on my dash. And for the rankings, so this is our stereocenter. That carbon is ranked first, that one's second, that one third. So in this case, we do have a clockwise rotation. 4 is in the back, so that one's R. So we have 3R, 4S. So writing this in here, 3R, 4S, and 3-methyl-4-heptanol. All right, for the next we have 1, 2, 3, 4, 5, 6, 7 carbons again. So this again is going to be heptanol. The alcohol is the parent, so we're definitely going to start on this side and give that alcohol the lowest number possible. So this is going to be 2-heptanol. And we have bromine at carbon number 1, 2, 3, 4. So 4 bromo 2-heptanol. And then for the stereocenters, here we've got bromine. That carbon chain is going to rank second. That's third. 4 is already in the back. So that's an R rotation. So this is going to be 4R. And then for this carbon right here, oxygen wins. That carbon chain second. That one's third. 4 is in the front. So it's a counterclockwise rotation. So normally S, but 4 is in the front. So that's going to be R. So 2R and 4R. So we have 2R, 4R, 4-bromo 2-heptanol. All right, for this one, we need to prioritize our alcohol being part of the parent chain. So this alcohol needs to be in the chain of carbons we are going to call the parent chain. So in this case, we have 1, 2, 3, 4, 5 carbons in our parent chain, and that's the max length we can get when alcohol is part of the parent chain. So we have to disregard the fact that we have 1, 2, 3, 4, 5, 6. We could make a hexane parent chain, but if that was the case, the alcohol would not be part of the parent chain. There is a way to name that, but I want you to instead basically just make alcohol part of the parent chain because it's easier to name it that way. It's also the IUPAC standard for naming. If you have an alcohol functional group, you can make that part of the parent chain. All right, so for this, we have carbon number 1, where alcohol is, and carbon number 2, which is a stereocenter, and also has an ethyl group off of it. So this is pentanol, where alcohol is at the 1 position, so there's no need to number it. We have an ethyl at the 2 position, so 2-ethyl pentanol. I shouldn't have put a dash right there. I just wanted to fill space because I was writing backwards. So 2-ethyl pentanol. And then, like I said, we have a stereocenter right there. So with this, we have a carbon with an alcohol attached. So that one's going to be ranked first. We have our hydrogen in the back. This propyl group is longer than the ethyl group, so our additional CH3 is going to outrank that one. So this is an R stereocenter. So R 2-ethyl pentanol. All right, for this compound here, this actually is not a stereocenter and neither is that, because thinking about ranking, if we are figuring out which CH2 attached wins. If we keep going around, that's the same, and if we keep going around, we end up with the same carbon. So these are not stereocenters, even though they are presented on a dash. This alcohol is presented on a dash, and this is presented on a wedge. We do have a cyclohexane chain where alcohol is at the 1 position. It's the parent, so we're going to call it cyclohexanol as the parent name. And I will go ahead and insert the 1, even though it's optional for this. So I haven't put it right in front of the OL, so I'll do that in this case. So cyclohexane 1 all. And we have a methyl group at carbon number 1, 2, 3, 4. So 4-methyl cyclohexanol. 4-methyl cyclohexanol. Now, one thing we could do to specify the relationship between the alcohol and the methyl group is say that these are trans relative to each other. So if we wanted to specify this, we could insert trans, so they're on the opposite side. If we imagine our chair structure, or just looking at the fact that this is on a dash and that's on a wedge, and that would specify the relationship between the two R groups we have on our ring. But this I would accept for methyl cyclohexanol for your answer.